So the first topic in two-variable analysis is the correlation coefficient as represented by an R. And the value of the correlation coefficient is it takes two data sets, an X and a Y, and it gives you a number to represent how well that set can be represented by a line of best fit. So I've provided a data set for you here. There's 5 numbers on the X and 5 numbers on the Y, and I have plotted them for you. So 2 on the X, 4 on the Y is here, 4 on the X, 6 on the Y, 6 on the X, 5 on the Y, 1 on the X, 5 on the Y, and 8 and 6. So if you look at these dots, there might be a line going through there. It is a little bit, but you couldn't connect them all with a single line. So this correlation coefficient is going to give you a number that lets you gauge how well these dots fit the line of best fit, which we're going to end up calculating in the next video anyway. So the first things we're going to need to do this are our summations from the standard summation table. So I'm just going to extend this a little bit there. So when we were doing one variable, you needed to get a standard deviation for x. So we're going to have to do that now. So I'm going to need to know the x value squared. So 2 squared would be 4. 4 squared is 16. 6 squared is 36. 1 squared is 1. 8 squared is 64. Now, we employed some fancy tricks for trying to chop up data sets to make it a little faster. That's not going to work with this particular type of data because you can't divorce the X from the Y. If I start separating the two, then all of this information gets lost. So unfortunately, if I have repeats, like I'm going to have here, I'm going to have to actually do it twice. I don't just get to tally how many times they show up and add them that way. That said, now that I've got this piece to do my standard deviation in X, I'm going to need to do the standard deviation in Y. So I will need a Y squared as well. 4 squared would be 16. 6 squared would be 36. 5 squared is 25. And again. And 6 squared is 36. And a new quantity that we're going to calculate for the first time today is called the covariance. And the covariance needs to have the value of the x multiplied by the value of its y partner. So in this data point 2, 4, I'm going to take the x value, multiply it by the y value. So 2 times 4 is 8. And then I'm going to have to do that for every single row. So 4 times 6 is 24. 6 times 5 is 30. 1 times 5 is 5. And 8 times 6 is 48. So now that I have those done, what I'm really after is the summations of each column. So through the magic of low technology, just slide that over here, the sum of my x values, 2 plus 4 is 6, plus 6 is 12, plus 1 is 13, plus 8 is 21. The sum of my x values squared is 4 and 16 is 20, plus 36 is 56, 57, 61, 121. My sum of y, 4 and 6 is 10, and another 10 and 6 is 26. Sum of y squared, 16 and 36 is 52, plus another 50 is 102, plus 36 is 138. I'm just going to check those. 36 and 36 is 72, 82, 88, 50 is 108. Good. And the last one, the sum of x multiplied by the y coordinate 8 and 24 is 32, plus 30 is 62, plus 5 is 67. It's 107, 115. And again, through sorcery of low technology, I'm just going to get rid of this for a minute. All right, so we're going to launch into this analysis doing the two calculations that we've done many, many times before. We're going to get the standard deviation of x and the standard deviation of y. So if I start with my formula, then my standard deviation of x would be 1 over 1, 2, there were 5 data points. 5 times the sum of x squared is 121, minus the sum of x squared is 1 over 5. 605. Minus 21 squared, I believe, is 441, but we're going to be extra sure so as not to sow confusion. 21 times 21. Ah! 441. Alright. And since I have it out here, 605 minus 441 is 164. And if we're done, since we have the calculator out anyway, I'm just going to render that down as a decimal. The square root of 164 is 12.8 divided by 5 gives me 2.561. Lovely. So I'm going to add that to my list of numbers over here. And then I'm going to do some tactical erasing, because I'm about to go through and do the standard deviation of y, and really in all this work, I just have to change this so that it's a y value. If that's y, then I'm going to need the sum of y squared, and I'm going to need the sum of y. So if I were to quick erase these numbers, I can fill them in and I don't have to rewrite the entire formula again, so indulge me while I do that. Alright, so to continue with standard deviation of y, the sum of my y's squared would be 138. My sum of y's before they're squared is 26. 5 times 138, let's just check with the machine, is 690. 26 squared, 676. 690 minus 676 is 14. And the square root of 14 divided by 5 is 0.748. Lovely. So I'm going to add that over here. All right. So if I were to bring this data set back up here and cover my face with it, do you notice that the x values range from 1 to 8, and so they have a fairly wide standard deviation? The y values only range from 4 to 6. That's a much tighter distribution of data points, and look what's happened to their standard deviation. It's much, much smaller. So that shouldn't surprise you. Now that I have those things done, I need to calculate what's called the covariance, and it has its own formula, and it's going to need some space, so I'm going to make some. So to calculate this thing called the covariance, this one, in order to show that it is a measure of both x and y, I'm going to use the sigma again, because it's talking about spread and what have you. X, y, so I can see it's in both, is the number of data points, and that means the number of pairs. So in this data set, while there were 10 numbers I was working with, right, 5 x's and 5 y's, each pair requires an x and a y, so there are only 5 pairs in my list. So this number is going to be 5 when I get there. I need the sum of the product, which is why we did this on the charts, minus the sum of the x multiplied by the sum of the y divided by n squared. So for this one, as I said, there were 5 pairs in the data set. The sum of xy was 115. The sum of the x's was 21, and the sum of the y's was 26. And n is 5. 5 squared would be 25. So my covariance then is 5 times 115 is 575. Minus 21 times 26 is 546 divided by 25. So 575 divided, or minus 546, is 29 divided by 25 gives me 1.16. There's another number I'm going to add to my list here. So what does that number mean? I can't really tell you. It gets bigger the bigger the x value's range is. It gets bigger the bigger the y value's range is. And unless you scale it back down using these standard deviations, it doesn't really mean anything. So I'm going to erase this work, and then we're just going to use this one to generate the correlation coefficient, which, as the title suggests, is the thing that we were after in the first place. All right, so finally, in order to get this correlation coefficient, this thing is it's like a measure of the area that this data spreads over, kind of. So in order to boil that down into the correlation coefficient, I'm going to take, so R equals, this covariance, and I'm going to divide it by the standard deviation of x, so that's how wide that rectangle is, and the standard deviation of y, which is how tall that thing is, and I would end up with 1.16 divided by 2.56 divided by 0.748. So 1.16 divided by 2.56 is 0.453 divided by 0.748 gives me 0.606. So I'd like you to take a look at this number, and while I erase this here. Alright, so I'd like you to look at these dots here and notice that they don't really line up. And when they don't really line up, I get a number that looks like this for the correlation coefficient. Now, we're going to do another one shortly where the dots are very close to being aligned. And the better they are to lining up on one line of best fit, the closer this number gets to 1. Or, if it's tipped downwards instead of upwards, it will approach -1 as the line gets better. So just let that boil over in your brain for a minute while we erase this, and I'll set up a new data set, and we'll try one to compare. So here's the second data set we're going to consider. This one if you notice, looking at the grid, it has a much more linear shape to it. It's also decreasing. As x goes up, y is going down. So we're going to run through this whole correlation coefficient calculation one more time. And at the end, because it's more linear, I should be expecting a number closer to 1 as my answer. And because it's headed downwards, I should be expecting a negative. So when I'm done, and I haven't done this one yet, so here's hoping, I'm expecting a number somewhere around the negative 0.9 range. Now, this is a long calculation, and you have lots of interesting things to do with your lives. So if you have a fast forward button on your brain and body, like I do, it would be wise to use it now. So here we go. So now that we're to the correlation coefficient part, I'm going to take my covariance and divide it by my 2 standard deviations. So I have negative 5, with a nice round number. Standard deviation of x at 2.561, and standard deviation of y at 2, which is another nice round number. I end up with negative 5 divided by 2.561 is negative 1.952 divided by 2 gives me negative 0.976, as expected. So the fact that it's negative, if you were to do this on a random set without seeing it first, this negative is telling you that as x increases, y is dropping. So the line should be pointed like this. This portion of the number, the 0.976, is letting you know that this is very close to 1. And because it's very close to 1, those dots are almost on a line. In fact, if you want to represent this number as a percentage of linearity, so what percent linear is it, you can take this correlation coefficient and square it. And you would end up with 0.953. And this is the number here that's quoted on a spreadsheet, or anytime you ask for how well a data set fits the line of best fit you've drawn, they quote you the R squared value, which is saying that it's 95% linear. So if you had plotted these dots, and let's just get this up here just to look at it. If I try and draw a line like through the middle here, those are almost all on it. And I didn't even have to try hard to figure out where that line of best fit would be, because it clearly went through with the 2 of them. Like 2 here and through 2 there and right through that one. So this number here is reflected in how close to that line those dots are. We could do another one, but I'm going to leave you to try some in the exercises. So sometimes this number is really terrible. It's somewhere around 0.0 whatever. And if you get a number that's less than 0.6, really, certainly less than 0.5, then what the algebra and the calculation is trying to tell you is that this data is not a line. So if you try and draw a line of best fit through it or calculate one, you can do it, but you shouldn't, because there's no point in modeling something with a line if it is clearly not a line. And this number here is giving you a numerical value to judge whether something is linear or not. So I'll let that boil, and we'll see how you do.